and I'm the lead for the Trees Around the Globe student research campaign, and I'm the tree science lead for the NASA Globe Observer. So we're going to talk a little bit about globe trees today. You can see here greenings, clinometers, the importance of greenings, clinometers, cell phones. I know you probably did some carbon estimation stuff, so I have one slide just kind of rehashing some of that and how, we do it on the NASA side with lots of, pretty simple equations and things like that. And then I'm just basically going to be talking a bunch about some of NASA's Earth observing missions, specifically missions that tie into looking at trees and looking at the height of things on our planet, and being able to identify vegetation, trees, and all these things green on the planet. And we have lots of online tools that that we use at NASA to help visualize the data that we get instead of having to deal with raw data all the time. We have what's called level 3 and level 4 data, and we can visualize it on different things. And I'm going to show you an online tool called Open Altimetry. And that's one where you can compare tree height observations that you do on the ground through, using a clinometer or using the NASA Globe Observer Trees tool, and compare it to the NASA ICESat-2 mission's observations and measurements of tree height from space. So what you're looking here at this image here, this background image is showing you just Ireland, but it's showing you from the globe the visualization system. So it's showing over the last year the different observations that have come in for tree height and land cover. And you can see there's parts of the country that we would love to see more, but we have in certain areas, parts of Dublin and lots of areas you can see towards the West Coast where we have observations coming in from students and citizen scientists alike. So I want to share this one. It's very cool to share with you folks in Ireland. Is that this was one of the rarest images we've ever gotten of basically Ireland, England, and Wales and all these. But you can see it's basically a cloud-free day over Ireland, and I'm pretty sure you don't get a ton of those. So that's why this is such a rare image. The only little bit of cloudy stuff you see is you can see right in the center, you can see there's a little smoke trail from some type of fire that was in a wooded area there. But if you look here in Ireland, you can see it's basically cloud free, which is just a really cool. But this is the type of image that we deal with at NASA. You can see the greens, you can see where the forests and vegetation are. You can see the marine layers of clouds. You can see the oceans, and where you see these light blue swirly things in the ocean, that's where the phytoplankton blooms are, which phytoplankton, as can either tell us if the ocean is healthy or the ocean is not healthy where they're blooming, because sometimes we get these harmful algal blooms that are misrepresented as phytoplankton blooms. So as you can see though on this type of image, these are the type of images that we really look at NASA to see what's going on in a region or in a local environment. And then we like to compare these over time. We really look at change over time with a lot of our satellites. And that's what we're trying to do also with observations, with trees and land cover and things like that through the GLOW program. We're looking at how things have changed over time. So today, as I mentioned, we're going to talk a little bit about tree height and greenings, focus on some of the missions that I work on that are relevant to tree heights and greenings and land cover and things like that. Just a quick overview, and I know you know about the Globe Observer Trees tool. Just a quick overview with that. Just some things I like to say that makes the observations very important. A little quick slide on estimating carbon and how we do it. And then we'll go on to the Open Altimetry online tool, and I'll show you that, and we'll look at that directly. I wanted to show this because this is something that we often call like the pulse of the planet, and this is going to show you basically the global green up and green down, and you'll be able to see this because up at the top left here, you see a date. It says vegetation index 16-day Terra Modis. That's the satellite and instrument that is getting these observations in this data. And then we have the date, and you'll see how it changes from spring basically you'll see the seasonal change in the in this, which basically you're going to see this pulsating green, which shows you, the green up, in the spring in the northern and southern hemisphere. Then you see the green down. You can see it alternating throughout the year. So let me play this here. There's no sound with this one, but I just want to showcase this. This is a super cool animation too, because you can really see basically how the earth breathes. You can see Ireland stays relatively green. It kind of goes from a light green to a dark green versus some areas, in the United States where I am, it goes basically white where there's snow cover, where the green is, the deciduous trees have lost their leaves. The pines are dormant, and they're still there, but they're dormant, so photosynthesis isn't happening as much. As you can see here, seasonally, you can really see these greenings. And, this is that global picture that's super important to all of us. But the observations that you take and, students and citizen scientists take, those local observations combined with these global observations really make for, a much more robust data set. So looking a little bit at trees and tree height, greenings, and some clouds. First of all, let me pause a second. If anybody has any questions or anything about that, about this graphic or anything else before I jump into, a little more in depth of why the tree stuff is important.
Is that just a graphic, or is it actually aerial photography? The green up, green down.
Oh, so this here is basically processed satellite data from the observations. So this is all from satellite data, and it's a composite throughout this time frame, getting the global coverage. So every time the satellite, makes a path, it creates this swath and collects this swath of data. And when we get all this data for this time frame, we can pop it all together in a map like this to basically, it's kind of like a, how should I say, it's a satellite time lapse, basically, where we're a satellite time lapse composite where we're taking all these images that were taken from the Terra Modis instrument, and a combination of, the greenness. So what the satellite is doing is we're getting pictures from Terra of the ground, but then the Modis instrument on the satellite is basically measuring reflectivity, which then in turn allows us to get the greenness of, the ground surface. So then we combine these snapshot images with the greenness, and we're able to create this fluctuating map like this, showing you the seasonal change in green.
It's the overall mission of GLOBE, and it's the green. It's a overall overarching mission with these projects and the satellite connection for the world.
Can you hear that, Brian?
It was hard to hear. Yeah.
The overall mission of the project and the program.
You mean the trees mission, or just kind of?
Well, both really. Just like, is there this global focus? I just want to know what is the above.
From a NASA context, like why do they?
NASA and their objectives.
Yeah. So that's good because the GLOBE program is funded primarily by NASA. So, what NASA focuses on, like NASA has, specific campaigns. They focus on certain things during the year, even though these satellite missions are in space, 24/7, taking observations all the time. However, how NASA sets up their observations and their focuses, during a year, GLOBE, kind of follows that direction because, GLOBE is funded by NASA. GLOBE is also funded by NOAA, the National Oceanic and Atmospheric Administration, the U.S. State Department, and the National Science Foundation. So GLOBE is a global effort, of course, basically 127 countries, and it's a combination of, where we want the students and citizen scientists and teachers to take these local observations and then do comparisons, to make sure we know basically what these local environmental measurements mean for the larger picture. And this larger picture is what we get from NASA satellites and, even like airborne campaigns as well.
Is that for ultimate interventions or to identify concerns, or is it, or just
Yeah,
when?
yeah, it's basically, to provide data. NASA, specifically NASA is a science agency. We're not a policy agency. We don't, you know, make recommended policies and things. We provide, when we provide, we see something happening, we provide that data to the right parties. So yeah, we don't suggest policy. We don't suggest what you do with the data. We can help out with that, of course, because we have the data. But it's very strict federal government protocol in the United States, where NASA is a science agency and not, a policy, agency. But we provide data to policymakers who then can figure out, and with our assistance, figure out, the best use of the data in, mitigating whatever they need to mitigate or learn more about. And the GLOBE program is kind of like that too. We have this data. We're providing data for student research, for researchers in the field. We have the GLOBE program has about 250 million points of data that have been collected over the last, 27 years since GLOBE started. So that's a lot of data in the database. So, we're hope to provide that data to anyone who needs it. And there's been lots of folks out there who, students who have done projects where they've taken it to their local, local community leaders, local government. For instance, I know there was one in Croatia probably about 5-6 years ago where there was a local park, and the park, people were having breathing issues in the park, and they realized it was an invasive species that was affecting the lungs of people going through that. They were releasing these spores into the environment in this park, and this was an invasive species. And they found this out because people noticed this, and some students with the GLOBE program in Croatia went and did, air quality studies and did particulates and things like that in this area. And they found these high concentration of these particulates, which were affecting people's lungs and everything. So they went to the local government there and said, "Hey, we think we know what it is," and they eradicated these invasive species, and the park's flourishing now, and people are enjoying the park again. So that's just one real world application of, how you can use that data locally. But if anything like that happens in other parts of the world, they can say, "Hey, there's already a group in Croatia, a bunch of students that took this GLOBE data and provided this, and maybe this is something that's happening here too."
That's great, Brian. Thanks.
All right. So looking at trees some more, I always like to show this because this shows you why tree height's important. Because a lot of people think, oh, they look outside at a tree and like, oh, great, it's a tall tree, it's a small tree, big deal. What does that matter? Well, tree height is the most widely used indicator of an ecosystem's ability to grow trees. Let's take two places on the planet that are, pretty much opposite. Let's take the Amazon rainforest in South America, and let's take the Sahara Desert. If we look at an area like the Amazon rainforest, it's an area where there's lots of trees, lots of tall trees. And why is that? Well, the ecosystem has that ability because it has the right soil content. It has that really rich humus, that organic soil. It has the right climate, that climate where it's humid. There's a great amount of precipitation. The temperature stays the same. It's a moist climate, so we get all these trees, lots of these trees growing. Conversely, you look at the Sahara Desert, not many trees, not a great environment to grow trees. We have sandy soil. We have, very, minimal precipitation. We have a hot, dry, arid climate. So not a great place. So where you see these areas where there's lots of tall trees, that environment really has a really rich ecosystem, as far as the ability to grow trees. And also tree height allows you to track the growth of trees over time. That's just a simple concept. You probably have a favorite tree that you've seen, one that maybe know from your childhood, or, around your local park or something like that, where you've been noticing that, oh, it's getting taller, or perhaps, it fell, or you notice some parts of it is dying out. But by looking at just tree height, you can also determine, the health of a tree as well. But also, with all that information combined, scientists really use that data to help us understand the gain or loss of biomass, which can help us understand how much carbon is being pulled in by trees and stored from the atmosphere. Carbon gets sequestered by trees, on a global scale. You know, we have 3.03 trillion trees on our planet with 78,000 different tree species. All of these pull in carbon and sequester carbon at different rates based upon the tree species, the size, their location, how much carbon's in the atmosphere, things like that. We have the Arctic boreal landscape, you know, up in, you know, the northern parts of northern latitudes where we have literally millions of these pine trees and they're really pulling in lots and lots of this carbon dioxide from the atmosphere. That's why places like, you know, big cities like all over the world, you know, we have areas like, you know, Los Angeles in the United States, New York City, you know, even Dublin in Ireland. We're always getting these cities that are starting all these tree planting campaigns, whether they're greening roofs or, you know, planting trees around along the sidewalks. You know, one reason is it essentially makes the area cooler. Okay, but also it pulls in a lot of that carbon dioxide that is hovering over these big cities where we see more people, we see more cars, we see more, you know, buildings and lots more energy being used, where we get that more of that carbon dioxide in the atmosphere. So that's helping to do that as well. And then NASA has a bunch of missions that are actually looking at tree height from space. And one of those is ICESat-2, the Ice Cloud and Land Elevation Satellite 2, and also an instrument on the International Space Station called JEDI, the Global Ecosystem Dynamics Investigation. And I'll get to that in a second. And if you're happen to be Star Wars fans out there, you know, JEDI is a play on that. And the funny thing about it is it's JEDI, may the forests be with you. So it's pretty corny, but, you know, we are NASA scientists, so, you know, we kind of get into that whole science fiction thing. So, but yeah, so I just wanted to showcase that a bit. Here's something I want to show you a little bit about, you know, the importance of greenings. Okay, because greenings, you know, the green up, green down protocols that we have with the GLOW program. Green up is in the springtime when the leaves start coming onto the trees. We start getting some bud burst. You know, the trees start, you know, coming out of the dormancy from, you know, an increasing photosynthesis. And then conversely, we have, you know, in the fall, in the winter, we have the green down where, you know, the deciduous trees lose their leaves. You know, the pine trees start going a little more into dormancy stage. But what's cool about this is that, you know, green up, green down, we've noticed that, you know, we know that scientists use green up and green down to study these seasonal cycles of plant growth. And what we're seeing very often now is that these planting seasons around the world have been shifting. You know, sometimes, you know, it's warmer earlier in the spring or even like late winter where, you know, around here in Maryland where I live, we have a huge agricultural area. We have lots of corn and soybeans and wheat, and we have lots of watermelons and strawberries, blueberries, things like that. But, you know, last year I noticed I was driving to my in-laws' house, and it was the middle of February, and they already had the irrigators on in one of the fields, and they were actually growing sod. They were growing, you know, grass that people use that they pull up and then use to, you know, when they're building a house and they're putting in a brand new front or backyard, they lay this sod down, you know, instead of, it's a little more expensive than planting grass seed, but it's, you know, it's like instant grass basically. So we noticed that in February they were growing this, and I don't ever remember this before being this early in the season. So, you know, we've really noticed that these planting seasons and even the harvesting seasons at the end of the seasons have changed. I've talked to some local farmers, and, you know, it's kind of a bittersweet thing where, you know, they see that this is changing, and sometimes their crops are you know, suffering because of, you know, we're getting more heat and more direct sun in some areas here, so some of their crops are dying off. But they're able to plant more crops throughout the year because they can start earlier in the season than they did 10, 20, 30 years ago. So it's kind of a bittersweet thing. And a lot of these farmers are using like actually some NASA data to try to figure out when the best place to plant. So, you know, we're looking at this whole global warming climate change things when it talks about this, and you can see here some of the observations that we've gotten. You know, this is how they come in through the GLOW program. You see on the left side, you know, you go in there and we take an observation. You can identify the genus and the species of trees. You can then, you know, follow this tree over time for the green up green down protocol, and you can see here on the top one we have different stages of this where there's green up, where we have dormant. So basically nothing's really going on. We see what's called swelling. So it's about to start doing this green up. So getting ready to, you know, burst. And then we have a bud burst. And then we have this change that happens, what's called this measurable change. So this we see that's where we see the greening, and we see this spring greening. And then you know, and then we have the opposite. We have, you know, these just happen to be green up, but then green down, we're going to see that trend kind of shift down the other way. I don't have a graphic for that. Sorry about that. I just have two green up ones here. But you know, looking at these greenings and seeing how greenings are changing in your local environments, the shifting of green up and green down, you know, dates throughout the year, from year to year, it really helps scientists looking at that global picture of where things are changing at different rates than they were in the past. Let me pause here a second too, and then I'm going to hop into a little bit about these satellites that we can measure these type of things from space. All right, let me continue with lasers from space. And as I mentioned, these are the two major ones that can actually measure tree height from space. You know, JEDI's primary objective is looking at tree height from space, just tree height in a specific area on the map, on the globe. ICESat 2 can look at tree height, but it's not its primary objective. Its primary objective is looking at the melting ice in Greenland and Antarctica and Alaska and the Arctic and Antarctic regions. But because it's a laser altimeter, meaning that it has an instrument on board that can measure height. So it fires off these laser pulses from the satellite to the Earth and then back again, and we calculate the time it takes to do that. And I have a short video about why lasers in space and why they're so efficient. And this video will talk briefly about, and there is sound and narration in this. This talks about, you know, how we started doing laser altimetry, this is called LiDAR, light detection and ranging, you know, on other planets and looking at moons and things like that to figure out some of the characteristics of, you know, like the moon and other celestial bodies. But then we also figured, hey, we can do this on the planet too. We can do this on Earth, which we really need to look at that third dimension.
If you wanted to find out how tall mountains are on other planets, how would you do it? If you're on Earth, it's easy. You can take a picture, fly over the mountain, or you can actually go there and measure how high it is. On other planets, it's much more difficult. You might be able to estimate height using shadows, or even take 3D pictures from a satellite. But what if you wanted to know what the mountain looked like as a 3D model? To find out, NASA scientists can use a precise measuring tool called LiDAR. Mounted on a satellite orbiting high above a planet, LiDAR instruments are able to accurately measure the distance between the instrument and the landscape below using laser pulses. To make these measurements, the LiDAR instrument first sends a laser pulse down to the planet's surface. The pulse hits the ground and reflects back to the instrument, where an onboard counter measures the time it took the pulse to make its trip. That gives a precise measurement of the distance between the instrument and the ground with respect to the planet's gravitational center. As the satellite passes over the landscape, the instrument sends out a series of regular pulses. By recording and combining these measurements, scientists can use the instrument to gradually build up a map of the height of the terrain. After many more measurements, the end result is a high-resolution 3D model that scientists can view as if they were actually on a planet flying over the terrain. They can then study its shape in more detail, looking for clues to the relative ages of craters, the shape of valleys and landscape features, and much more. But LiDAR is far more versatile than simply measuring the shapes of mountains and craters. Earth scientists, for example, use LiDAR to measure the height and density of the Earth's forests. Others use LiDAR to study small changes in the heights of the Earth's major ice caps over time. Still other scientists use LiDAR to study the composition and structure of Earth's atmosphere, as well as the atmosphere of other planets. And they can do all that without ever having to climb a mountain.
So that just showed you a little bit about lasers in space and, you know, why we're using it, why they're efficient. So ICESat 2 is Ice Cloud and Land Elevation Satellite 2, and as you can see, its primary and science objective are looking at the melting ice sheets, you know, of Greenland and Antarctica and how this affects sea level rise, and then also the massive ice sheets and glaciers, sea ice thickness. Sea ice is basically just frozen salt water. That's what we find in the Arctic and surrounding the Antarctic Peninsula, as well as excuse me, measuring the height of vegetation, forests, and other ecosystems worldwide. So since we have a laser altimeter, we're able to get that third dimension. So with that said, you know, ICESat 2 uses LiDAR. but it's what's called a near polar satellite orbit. So it moves around the North Pole and the South Pole at what's called 88 degrees north, 88 degrees south. It doesn't go directly over the poles. It goes over the angle based upon the its movement and the angle of the planet. So, basically, as I mentioned, what we're doing is we're calculating the time it takes the laser pulses to leave the satellite, bounce off an object on Earth like a tree, and then return to the satellite. And when we do that repeatedly, we can figure out how tall those trees are. And I'm going to show you, as I mentioned earlier, this thing called open altimetry in a couple minutes about focusing on how we can look at it. We're just going to zoom into Ireland when we do that use that online tool, so I can just show you the possibilities with that online tool. So how is this done? And this, I have several videos here because at NASA we like lots of visual stuff. But I want to show you this. This is one. This is with my engineer colleague Phil Lors, and he's the deputy engineer who is in charge of the building of ISAT 2. But what they had to do was they had to figure out, how to be precise, as precise as possible, and they figured it out to within a billionth of a second. So what that means is if they're accurate to within a billionth of a second with these lasers, they can detect changes on the ground as small as 2 centimeters. So if the ice grows or shrinks 2 centimeters, we can determine that. Same thing with trees. If we see a tree growing, we see that the top of the canopy has grown, 2 centimeters, 3 centimeters, 4 centimeters, the satellite's able to detect that. And this is how it's done, because you might have questions like, how do you, since you're firing laser light at the planet, how do we know that those laser lights that are coming back from the Earth to the satellite are actually the ones that we sent from the satellite and not from other sources of light on the planet or even the sun or other celestial bodies? And this kind of gives you this does give you the answer why, with a little background.
The Atlas instrument on the ISAT-2 satellite measures elevation by timing the flight of laser light pulses that leave the satellite, bounce off the surface, and return to Atlas. The speed of light is very fast, and so a regular stopwatch would give us too wide a range of time, a big margin of error. The timing has to be ultra precise, less than 1 billionth of a second, in order to measure the height of the surface within just a few centimeters.
I'm Phil Lors. I'm Deputy Instrument System Engineer on the Atlas instrument on the ISAT-2 mission. Calculating the elevation of the ice is all about time of flight. It's time of flight of the photon from the laser down to the surface of the ice and back. So what we are doing is creating time tags of the transmit when the laser fires and time tags of the receipt of the photon. So it all starts with the transmitter. When the laser fires, it puts out billions and billions of photons. We pick off a little bit of that and we send it to a detector and we produce a start pulse. And that is the start of our timing system. The spacecraft sends us a position and attitude message every second that tells us where we are in the orbit. From that, we calculate where we think the spots are on the ground. We have a rough database of the whole Earth with elevation as it travels up and down mountains and down into valleys and over ice sheets. For each spot, we calculate where we think the surface is, and we open up a range window. For every photon that's received in that range window, we produce a time tag. Now, the sun produces a lot of green photons too, many more than our laser does. So our laser produces billions and billions of photons with every shot. If you add the noise in there, you won't be able to tell the sun's photons from the laser photons. So if you just took one shot, the one laser photon would be lost in the noise. But if you take 200 shots, now finally you have enough surface signal coming out of the noise that flight software on board can pick out this is noise and this is the signal from the surface. Once we downlink the photon time tags from the receiver and the transmitter, and we have the range windows, we put those all together, you have the transmit time tags, you have the time until the range window opened, you have the receive time tags in the range window. You calculate all that put together gives you the time of flight of a photon, which ultimately gives you the distance between the spacecraft and the ground. So if you know where the spacecraft is, and you know the time of flight, you know the distance to the ground, now you have the elevation of the ice.
Technology that can measure elevation adds a third dimension to how we map our Earth and allows us to study change across the poles and beyond.
So you can see that was a super precise way to, to get measurements done, as far as getting that third dimension. And here are two examples of, some of the things that we're able to get. The top one is showing you off the Bahamas. And what you're seeing there, that line through the middle, that is the ocean surface. So the satellite sent these photons down and a bunch bounced off the ocean surface and then back to the satellite again. So we're able to map basically the height of the sea off the Bahamas. But underneath there, what you see, the darker lines, that it was actually able to map the bathymetry of this area off the Bahamas. So we're able to get the ocean floor mapped as well, because the water was super clear and super still at this location. Below this is Sequoia National Park in Central California, where you can see here we were able to map the elevation of the terrain. You can see the mountainous area here. But then also you can see these spikes, and these spikes where these yellow dots are, these spikes are the trees. So these are all these giant sequoia trees that are in this area in Sequoia National Park. So ISAT-2 was able to measure the top part of the canopies of these trees. You can see also some understory as well. But when we are able to do this, you can map out, basically the forest height in these locations. And as it was mentioned, that this satellite fires 10,000 laser pulses per second. So that's how we're able to get this amount of data, but then also be able to weed out the data, the light, the green 532 nanometer wavelength photons that are coming from other celestial bodies, specific, primarily the sun. So we're able to do this. So I'm going to skip that one there because I won't hop on this one. So secondary, we have this ecosystems dynamics investigation called JEDI. And what this does is this focuses on looking at the tree canopy heights only, but it's looking at it in the mid latitudes from basically, 51.6 degrees north to 51.6 degrees south latitudes. So because that is the orbit of the International Space Station. So what it's doing is it's getting a very precise measurement of just the forests in these locations and this forest site. And you can see how this is how it works. So it creates this 4.2 kilometer swath where it's constantly finding out how tall these tree canopies are. And you can see here, it's basically showing you the same type of thing. It's showing this LiDAR. It's getting this reflectivity off the top of these canopies to get these tree heights. Okay. So all of this stuff that I've been just talking about is how NASA does this, from space. All right. When we're measuring tree height from space, we necessarily don't like clouds. Clouds are something that we love, though, in the real world for the most part, because they essentially keep the planet cool. They provide shade, but we have nasty things come from clouds as well, like thunderstorms and tornadoes and hurricanes, things like that. But when we're talking about trying to measure the height of things on Earth, clouds get tricky. We have certain clouds, like the really thick clouds where the lasers can't penetrate, and then when we get missing data on the ground from that location at the time. We also had these really thin clouds called cirrus clouds, which you think wouldn't be an issue because they're so thin and high in the atmosphere. But the problem is they're made from ice crystals. So we get a lot of laser refraction happening, with these cirrus clouds. So, with NASA, clouds are good, clouds are bad, depending upon what satellite you're looking for, the data you're looking for. There's lots of satellites, that use this high-powered radar. You can go right through the clouds. All right, but with the light, with the LiDAR, the lasers, clouds tend to, cause some problems. And there are lots of algorithms written to, combat this and, try to figure out, the best they can, about, what the data is going to be. But, these areas won't be completely cloud covered all the time. So when the satellite comes over again, there's a great chance that we're able to get this data as well. And then the last part of this with the satellites, as you can see, we're getting a lot of amazing numbers in here. We've taken over 1 trillion laser shots from ISAT-2, over almost 25 billion from JEDI. And what we have here is we have basically the amount of photons that return to the satellite translates to data points. And you can see we have, 13 trillion photons returning to the ISAT-2 satellite. And we have 293 billion photons returning to JEDI. So we have lots and lots of data, for use for anybody. And all this data is available to everyone, just from the websites related to the missions. All right, let me pause here again, because I'm going to jump into a little more specifically about GLOBE and how we're measuring. And sorry if you hear dogs barking in the background, but my wife just got home from taking my son to summer camp, and the dogs get a little excited, even if we're gone for 30 seconds.
Any questions about the satellites in particular, or you're interested in?
Can I ask what height is ICESat? Like, what's its orbit?
So it's about just over about 300 kilometers above the Earth. And it has a near polar orbit, so 88 degrees north, 8 degrees south. And I should also mention, which I didn't, it has a 91-day repeat orbit. So basically every 3 months it hits the exact same spot on the planet. So that's when we're able to then compare that data on that exact location. Now, that doesn't mean it only hits that spot every 3 days, because, every 91 days, every 3 months. What it means is that the photon will be sent out directly above that location every time, every 91 days. But when that satellite, because that satellite is flying at that elevation, when the laser photon leaves the satellite, it's a small laser footprint. But when it hits the ground, because it traveled all that distance, that footprint spreads out. Okay. When it spreads out to about a 13-meter diameter footprint. So whatever trees are within that 13-meter diameter footprint, that photon that bounces off of that canopy, those canopy heights, what we're going to get back from the satellite is the average height of all the trees in that 13-meter diameter footprint. Because, if you just think of it, when you hold a flashlight up to a wall and you're standing next to the wall, you get a, pretty small circle. But as you back up, the further you go, the larger that circle gets on the wall, right? So when we're talking about, that far away from Earth, hundreds of kilometers away from Earth, that footprint is going to expand and expand and expand, that the diameter of that laser pulse.
And those 13-meter circles, I presume there's overlap then where pulses, so you can get more three-dimensional.
That's what I was. That's what I was alluding to. That you'll hit the exact same spot every 91 days, but you will always get overlap because of that 13-meter footprint. So that's why there's more than just one data point in that location than every 91 days. We're getting, multiple, basically multiple per month for that because of that overlap. Yeah, great question though. And, for the most part, when you're comparing the tree heights from like ICESat-2 or JEDI to, the GLOBE data, sometimes, the most part we get, a grouping of tree canopies where we get the average back. And on a rare occasion, and I'll show you a later one that we got, was when there's only a single tree in that photon footprint, which is super rare to get. But there's actually one I got in my neighborhood. We got an area where there's a forested area on my property where we got a photon that dropped on a bunch of trees. And then we got one on the other side of our neighborhood where there was a Bradford pear tree. It's an invasive species in our country, but they're pretty, but a lot of them are being taken down because they're invasive. But there happens to be one near a pond in our neighborhood, and there's no other trees for about 15, 16 meters away from it, and a photon dropped right on top of the tree. So we were able to get just that tree height observation, which is pretty cool to see because it doesn't happen often. Because there's lots of trees in my area, on the what's called the Delmarva Peninsula, Delaware, Maryland, Virginia Peninsula, where I'm driving by and I see an isolated tree, and then I mark where it is, and then I go into the database, the open altimeter, which I'll show you in a minute here. I go into that and see if there's a match, and there's rarely a match for an individual tree, unfortunately. It would be nice. So with that said, there's multiple ways with the GLOBE program, of course, for measuring tree height, and we have the tried and true handheld clinometer, basically that instrument using to measure the angles of slope and elevation, where basically you
Brian,
tie.
sorry to interrupt you. I'm talking across you for one moment. I'm just conscious that we do have another speaker coming, in a few minutes, and
Okay.
I'm just wondering, the teachers here, they spend a couple of hours before lunch using the handheld clinometer and then using the app, and so they had some practice. And I'm just wondering, since we only have about 5 or 6 minutes left, I
Okay.
wonder, would you mind if I throw it out maybe to a few questions, if they had any questions based on what they did this
Yeah,
morning?
that's perfectly fine. And then if we want to at some point, I can not today, but if you want to set anything up for some other time, we can go over that open altimetry thing a little longer. Some other, presentation at some point in school year, whatever, however you want to do it.
Yeah, that would be absolutely fantastic, because I know everyone is really interested,
Yeah.
and partly due to our technical difficulties at the beginning. But yeah, I guess if
Yeah,
I
let me
turn
stop
it
sharing
over.
and I'll just come back to the regular room so we can go through some
Okay,
questions
cool.
if anybody has any questions.
Excellent. I don't know if anyone has any questions from this morning, but I know there was a few kind of discussion points. If anyone to put everyone on the
So
spot.
did you all notice any comparisons or differences between using the clinometer versus the app? Did you see anything? You said that was done, like both of the were used?
Yeah, it's a bit of a range in our findings. Yeah.
Okay. Yeah, and we do notice that, especially when we first start doing that, when we were in Estonia, out doing the testing and then out doing the expeditions, that, we noticed that, some of the students were taking, kilometer measurements and getting really close with the nautical observer, literally, 2 meters and under, comparisons. But then we had someone who did one of an observation where it was a 20-meter difference, and which is a massive difference. And so we went. And the funny thing I found out is that they were using the clinometer upside down, which I don't understand how they did that. I'm not understanding how they read an angle or anything. They had the straw at the bottom, and the weight was hanging down underneath the straw on the. I don't understand how any of that worked, but we got them fixed up. But yeah. So what type of differences did you see? Did you see lots of like many meters difference in the heights?
It was less than 2 meter difference.
Okay. Now let me tell you
Yeah.
that's really good, because being a NASA scientist, I work with other scientist colleagues with ISAT-2, but I was talking to some of the folks who focus primarily their research on vegetation and trees, and they've been some of my colleagues from NASA and inside and outside of NASA. They're affiliated with the ISAT-2 mission in some way. That they say if we're able to get a comparison like that of, basically, 4 meters and under with trees, that's a really good comparison. And we say that because, with the ISAT-2 satellite, we get a lot of absorption in trees because, trees are green. The laser light coming from the trees is a specific wavelength, 532 nanometers. But for instance, if we get trees that match up to the color of that laser light, it's almost impossible to get the photons to bounce off of those trees. It'll get absorbed by those trees, by the leaves. So with that said, the accuracy of measuring tree height from space is a little less than measuring the accuracy of like ice and snow height from space, because we have what's called a high albedo on those white surfaces. We have that high albedo, so we get much more precise and a lot more photons back to the satellite. With the tree height, that's why we have this, within 4 meters. If, the lower the better, of course, but if it's 4 meters or less, we still have amazing data that scientists can use, from the globe database and do these comparisons to the satellite data to help give that, primary, secondary, tertiary level of data, for the research. And that's why, there's more professional papers being written using the globe science in comparison with the NASA satellite science. We just published a paper in June 21st where we compared, the ISAT-2 data to globe data in different parts of the United States, and then also to airborne data that a specific airborne campaign in Grand Mesa, Colorado was doing. So we actually compared the globe citizen science data basically the data was from Greenbelt, Maryland, Queens, New York. There were 76 high school students. Sorry, middle school. Well, I'm not sure. I guess it was high school students in the United States. Ninth grade is either middle school in some schools or high school in other schools. So where I went to school growing up in Pennsylvania, it was middle school, but I think in New York right now it's considered high school. Well, with that said, we had lots of observations, comparisons between the globe ground-based data to airborne data to space-based data, and we got really amazing matches. Within totally within 10% of, they were all within 10% of each other. Total. So it turned out really good.
Thank you.
That's fantastic, Brian. Thanks a million. Just on behalf of everyone in the Globe team, and I think all the teachers here, just thanks a million for joining us.
Sure.
And really, getting this insight and different perspective on trees, and just how that information is useful for NASA and other scientists is really valuable. So I'm sure we kind of want to give you a round of applause here.
Yeah, and feel free, please call on me if you want to learn more about the open altimetry and how you can compare the satellite data directly to the globe data that you're collecting with a clinometer or the app.
Sure, that'd be really interesting. I know there'll be plenty of people interested in hearing more about that. I hope you have a good day.
Yeah, thank you. You too.
Yeah.
Great to see everyone.
Yeah.
Right. Bye.
Bye.